Next up is the spring force. All right, clearly it's a force due to compression or extension of a spring. And a spring is what you think it is, just a coiled up piece of wire that is kind of stretchy. One property of a spring we need to think about is that any spring has a natural length. All right, so if we just take a spring, coil up a piece of wire like that, if you were to measure, you'd say, okay, it's at some length L naught. Okay? I'm going to call it L naught because the length is going to change. So we'll call that sort of the natural length or the resting length, just if you held it like this. There's your L naught. Now, if you take a spring like that and clamp one end, and the other end is the origin, well, we always draw our problems in physics, right? So we would draw it and say, there's a heavy wall, that means the clamped end. And here's our other end. And if I said the origin, I must mean to draw an axis, x-axis, and here's the end we're going to attach things to, and that must be the origin. Okay, so we set that up. I can actually set that up over here. Here's another spring, better for the demo. Again, just a coiled up, stretchy piece of wire. And I'll set it here, and I need to clamp one end and call that the origin, or call the other end the origin, right? So here is my clamped end. And for the origin, see, we're going to label and draw an axis here, plus x. And then here is where I'm going to attach it. In this case, means I'm going to grab it, so we'll call that the origin. So the way a spring behaves is that if we pull this now to positive x, so my fingers are going to apply a force, the spring is going to pull, I'll feel a force on my fingers, and which way is that force? It is in negative x, right? The spring pulls back. So if I pull and extend the end of the spring to positive x, push the force I feel, negative x. If I compress the spring, if I push the end of the spring to negative x, I feel a force, but this time it's pushing me back to positive x. So a spring makes what we call a restoring force. It has a position that it wants, the origin, and anytime you move away from that position, it pulls back. If you move to plus x, the force it applies is to negative x. If you move to negative x, the force it applies is to plus x. Because all a spring wants to do is be at its natural length. So if we want to write that in terms of physics, it's called Hooke's law, which is the spring saying, let me be my natural length. And it's desperate too, so I'll put exclamation point. Right? So Hooke's law then, F, and you put minus kx, where k is the spring constant. All right, and let's think about what unit the spring constant would have to be in. Well, if this is newtons and this is meters, then it's in newtons per meter. Okay. So every spring has some spring constant in newtons per meter. This one has one. This spring over here has a different one. And the spring constant is not negative. It's a positive value. It's just a property of the spring. But the negative sign we put here reminds us that the force is the opposite direction to the displacement. Okay? Now in most problems, or in a lot of problems, you won't really have your spring nicely laid out on a flat surface. Usually your spring is hanging like this. So now we'll put the spring on a rod. And pretty much nothing is different, right? It's just hanging. It's got the same natural length. But, again, there's usually more going on. Usually you have a mass on the spring. So here this little hanger has a, well, there's just the hanger for now. And you see what's going to happen when I let it go. The spring got a little longer, right? So it kind of looks like L naught is changed, but L naught can't really change, right? And that's a property of the spring. It's changed because this is pulling down on it. And then you'll usually have a weight on it, right? Like that. And now it's even longer. L naught is changed again, or the length of the spring is changed again. But there doesn't appear to be any force because this isn't moving. The sum of the forces on the mass is 0. So I just want to explain what you have to sort of think about when you hang a spring vertically. So let's take this same spring, and I'll just kind of draw it in the middle here. And let's now hang it vertically. And it's a lot longer because it has a mass on it. Right? So, well, the reason it's longer is because we are now pulling on it with a gravitational force. And we know F equals minus kx. So if we want this mass to not move, it's got a gravitational force pulling down. Therefore, the spring force has to pull up. If the spring force is going to pull up, then the spring has to extend down, right? So its natural length was about here, and by letting it get longer to here, it applies a force that wants to make it shorter. And that force that makes it shorter is balancing the weight, okay? So the spring does get longer in its sort of natural equilibrium position. And you can actually then, if you want to consider this the origin, you can still apply Hooke's law. You just, in terms of doing a problem, you just imagine this is now the natural length of the spring. The natural length has been increased due to the weight of this mass. But it's actually still true, F equals minus kx. If we now consider this resting position the origin, if I pull down, say this is positive x, it pulls it back up in the negative x direction, right? I feel a force on the mass pulling it back up. If I push it up, it feels a force pulling it down. Right? So it still acts like Hooke's law even when you hang it up vertically. And if you think about it, actually, if you pull it up a little bit, the spring is still pulling up. Right? It's just the balance between the spring force and gravity is what makes the net force pull down. Okay? So you don't have to worry too much about the details. I just want to let you know that when you put the spring up, you can actually apply the same equation, F equals minus kx, if you consider this the origin.